Great, thank you so much. I'm really happy to be here, and I really love talking about my research and also my journey kind of through computer science to where I am now. So I'm going to try to bring you on that journey, which includes a little bit of where I started in computer graphics and computer vision, and then how that all connects into accessible computing and helping people with disabilities interact with computers through computer vision and other technologies. Um, so I have a presentation. I don't know exactly how long it'll go, but I'm really happy to take questions afterwards, and I might skip some of the slides on here quickly, but you can ask me if you want to see them afterwards. Okay. So as I was trying to say, I just upgraded my whole system. So like I had some weird network issue and that my screen sharing is a little bit weird. So let me make sure that hopefully all works. And we'll talk a little bit about some of these things. So I'm gonna share like a whole PowerPoint screen and hopefully you can all see that. So does that look okay? Just because I have a new
Yeah,
setup. All right. So
yeah,
I can't do the full screen share, so this will be okay.
that's okay.
Um, so thanks. Yeah, I appreciate it. So yeah, feel free to interrupt. I see a few familiar faces here on the list. So if you've seen this before, hi, I see a few of you. Yeah, then that's okay. I did this a similar talk to the CS 120 class this past semester. So yeah, let me tell you a little bit about my journey. So I got into computer science originally because I liked computers and I liked video games, and I was really interested in like graphics because like having the latest graphics in a video game I thought was neat. And so that's sort of where I'll start, and then I'll talk about how I transitioned into computer vision and how where I am now. Actually, I can look back and see how a lot of these things connect to each other. So you've probably heard this phrase, a picture is worth 1,000 words. And the idea here is how do you describe an image, right? And so if we're in a classroom, I might pick on one of you, but for the sake of time, if you started describing this with enough detail that an artist could recreate it, how many words would you need? Well, would 1,000 words suffice? Probably not, right? You might get a picture, a painting of a dog and some water and some hills and some sand, but the amount of detail in here needs a lot more than 1,000 words. So a computer describes images as pixels. So you've all been doing some things with Scratch and then the App Inventor, right? And so you're a little bit familiar with like laying out um, of different graphical elements and how they interact with each other. But essentially, here we have small samples of what is in an image, and the idea here is, well, each one of these squares you might be able to describe as light blue or white or orange on this towel. And if you were to do that with a certain level of detail and sort of like a paint by numbers approach, right? Then you could recreate a system like this using the grid that I had overlaid. So this is what's going on inside of digital images. So there's lots of interesting things. This is the basis for all computer graphics and digital images, and colors represented with some amount of red, green, and blue. So you've probably heard of RGB, and maybe you've been using that already during this intro session when you're setting colors for things in your programs. So the idea is we represent samples of red, green, and blue colors, and these can be used to recreate images. So the neat thing is if I asked you without putting the slide up, what year was this picture from? It doesn't look like a picture that's 110 years old. Well, what the original images were, a photographer traveled around and took pictures on glass plates through red filter, green filter, and blue filter. And then this was a traveling exhibition. This is before they had color film that was really readily available. So you would go to an exhibition and they would project light through these three glass plates, and you could see this color image, which is the amazing technology of the time in 1911. So the reason I'm showing you this, the Library of Congress got a hold of the originals and they had to kind of do some restoration. They did a lot of digital graphics and touch-ups, doing a lot of things now that like your Instagram or Snapchat might filter your images. But at the time, right, so 2004, they had computer scientists, automating the digital reconstruction of these images. So to me, this is really neat. I'm thinking, um, I really like this image, but then I'm also thinking that there was computer science in here, right? So computer science was used to actually bring this all to us now and to start recreating it. So one of my big themes in my journey of computer science is um, going from a point where I was like, oh, technology is neat, and I like graphics because graphics are neat, to the point where I really started seeing connections with computer science and problems in the real world, and doing things that are beyond this is neat just because computer science people think it's neat, but this is useful for some problem in the real world. And we see this manifesting over and over in all sorts of different areas. And that's where I'm going to try to bring around to you today. This is a few years ago, right? So how many of you remember this? I don't have, I have this really big monitor now. That's why I can't do the screen share, so I can see some more of your faces. I'll make some more of you bigger. All right, I have like 6 of you with cameras on. All right, so many of you remember this, right? So I see it as white and gold. Oh, you have a hand. I have see a hand raised too. Man, I'm so rusty on my Zoom hosting, right? So if you have a hand raised, you wanna put a comment out or say something. Go ahead. And if you don't, it's okay. All right, I now have my participants, I have the video, I have my screen share. All right, so I saw this as white and gold. Other people, I'm sure you're sitting there saying, there's no way I see it as blue and black. So what's going on? Why, right? So this all has to do with perception. And one of my favorite web comics is XKCD, and they oftentimes do something that's related to pop culture and what's going on now. So this is a web comic from there, and what he's doing is he's demonstrating that actually these two dresses are the same color, but they look different depending on the background that they're um, faced with. And so earlier we were talking about red, green, and blue pixels. Well, you could load this up in an image editor and measure how much red, green, and blue there is, right? And so actually measuring the red, green, and blue of these different areas, well, these certainly look like blue patches. And I'm not sure what color gold is in RGB, but certainly looks like there's a lot of blue in this, even though I still see it um, as white and gold. So what's happening? Here's the question: what do you think is happening in the background? Does anyone just go ahead and unmute and um, where is this person? Like, what's going on? No one wants to volunteer. Professor Han, where is this person? Is this person? What's happening with the background, even if it seems obvious?
I don't know. Is it in the airport when you say like that?
Oh, yeah, I don't know. I mean, maybe that's not. I guess do we think they're outside? Do we think they're inside? Like, what's going on with the lighting in the background? So that's the big question, right? So I think why people perceive this differently is they're perceiving what's happening in the background in relation to the foreground dress in two different ways. So one way that you could perceive this is that we see this really bright washed out background, and therefore it's a sunny outdoor type of location, and the person in the dress is in the sun. Is there actually a person there? I don't even know. Okay. The other way that you might perceive this is that maybe the person in the dress or the dress is in the shade and that it's sunny behind them. Okay. And even if you can convince yourself consciously of one of these, kind of your subconscious perception is taking a hold of how you perceive what you're seeing. So we're going to start connecting in now to computer vision. Oh, and I see a chat. Let's see. Um, right, exposure to the right. It's either over or under. Yeah. So we don't know what's really happening, but our brain is filling in the blanks. So this is really actually related to important topics in machine learning and data science right now. This idea that um, we have some new information. The new information that we have right now is what we perceive, or sorry, what we see, right? These pixel values. But what we perceive is a combination of what we see now, the new data, along with what we have seen before, what our brains have seen before. And so I mentioned that maybe we think that the dress is in the sun, maybe we think that the dress is in the shade, and that has to do with how our brains have been trained to understand scenes, right? And so the human visual system is really good. It's much better than even the state-of-the-art machine learning right now. But all of this machine learning um, does the same thing. It takes new data, new observations that we see now, and relates it to what we expect to see based on what we have experienced before. Okay, so let's do one more, and this one's a little bit more interactive. Um, so are the top and the bottom of these tiles the same shade, or are they different? So you're probably guessing this is a trick. So the way to see this, the way to tell is take your finger, okay, and cover up the entire seam, including the shading on the seam, right? So that you can just see the top and the bottom. All right, I see a few of you doing it. All right, awesome. So when you do that, hopefully what happens if you cover up the seam, you see actually that the shading on the top of this tile and the shading on the bottom of this tile is actually the same, right? So these are the same shades, but they look totally different, right? And they look totally different because this top one looks darker, the bottom one looks lighter. So what's going on? We're perceiving something that isn't true. This is sort of an optical illusion. Well, why? Well, the human visual system has been trained to perceive things in the real 3D world. And there are clues or hints as to what we should be understanding about this scene. And this all has to do with coming from the shadows. So we see there's a shadow on the ground. We see there's kind of the shading on the bottom of this one, and there's shading on the top of this one. And what this is telling me is that there must be a light source up on top shining down on the top of these things. And so this one on top must be in full brightness of that light source. And the one on the bottom must be in the shadow, okay? And so our brain is then tricked into thinking that this one is darker than it is, and this one is lighter than it is, when actually, when you cover it up, it's the same, okay? So to me, this was a really neat insight to think about how optical illusions can tell us about how human brains get trained in a similar way that we train state-of-the-art machine learning systems now, right? And so all these things that you hear about, if you read about deep learning and neural networks, we're exposing a computer to data, to previous experiences, so that when we get new experiences, it understands how to understand them and how to perceive them. And even when we can trick our own brain incorrectly, we understand a little bit of how the learning happened. Okay. So yeah, so let me jump forward into some computer vision, then we'll get into some human computer interaction things. So obviously, I took some of this from a few different talks. You've been doing lots of computer graphics, right? You in everything you've done this intercession, you've been designing interfaces, art, games, animations, visualization. So all of that computer graphics, really useful things. And in some drawing approaches, what you're generally doing is essentially describing the geometry of what you want the graphics to look like. So this is some really basic graphics program that's basically says, let's draw a line between 2 points and fill it in with blue, okay? So computer graphics in general, the idea is you describe the geometry of a scene, and then you generate through processing a visual representation. Okay, in this case, I'm describing a line, and we generate the visualization of the line. And obviously, this can get um, a lot more complicated doing 3D graphics. You describe the 3D world using math equations for spheres and planes, polygon meshes. And this was some of the graphics I was really interested in when I got into computer science, because I wanted to know about like video games. Okay. Some of the things I was going to say, this is state of the art. So actually, I'm going to show you something from one of my homework assignments in 2001. So ray tracing is essentially a simulation, right? So a lot of the things we can do in computer science is simulate what's happening in the natural world, and we can do this to understand nature. And so we can do this to simulate things in physics and chemistry and biology. Well, ray tracing is is simulating essentially the path of light and how it interacts with different surfaces. Okay, and so I updated this slide right now. So long rendering time. So this scene over here is generated using ray tracing, and this approach is really good at dealing with things like reflections, refractions through different color, through different materials. So they're modeling the physical properties of how light would interact with these different materials, and you get these kind of photorealistic looking images. So I had on here long rendering time, but state of the art right now, 2020, 2021, is the current level of high-end gaming graphics cards can now do some of this in real time. And so if you're into high-end video games, right, and you want to buy a $1,000 video card, then it might be able to do ray tracing in real time, and you get this level of realism in your game that you're running through and playing. Okay, let's see. Okay, so here was my homework assignment, right? So I actually had to write one from scratch in 2001, and so it's obviously not as good as that last one, but um, I'm describing the scene. I'm just showing you a little bit of the code that describes the scene, but I had to write the code that actually simulated the light interacting with each of the surfaces. And I think this image, this scene here is describing the one in the top right. So I've created two spheres. I have a red sphere and a blue sphere, and then I have a green plane underneath. And then I have three light sources that are shining. One's kind of shining this way, so we see this shadow appearing on the red ball from the blue ball. We have another one coming up from the top, kind of creating this other shadow. And then we have one that's kind of like closer to where we are as the camera. So I thought this was kind of neat, and I liked doing the reflections. Um, I think I don't think I got an A. I think I missed a. I was supposed to be able to like put patterns onto things as well, and I didn't get that. So I think I had like a B plus. So just so you know, right? You don't have to be like you don't have to be the perfect computer science person and everything in order to become a professor. Let's see. So what else can I show you? So, oh yeah, oh, these are going to get messed up because I don't have the full screen open. But I really like whenever there's a new like Disney movie, Pixar movie that comes out. There's often some new graphics that happen to make the movie have some new feature, right? And so this was 2012 when Brave came out. The really new thing that they were trying to show was modeling the heroine's hair, right? And so I think some of these links are probably broken by now, but they talked about how the graphics artists had this big orange wig, and they wore it around the office, and they had mirrors on their desks, and they were like shaking the hair around to try to model how the hair worked. Okay, now fortunately pre-COVID I usually have much shorter hair, right? But from what I understand from talking to friends with a lot bigger hair, hair interacts with the environment, right? There's like you get like static. If it's humid, it gets more frizzy, and so they wanted it to be very realistic. And if you looked at like these animated movies before this, all the hair on the characters was very fake looking, and it didn't really interact with the world. But this was integral to this character. Um, let's see what else. This was Monsters University, I believe, right? And so showing how the graphics engine, they recreated how they did lighting. And so if you look on the left-hand side, Monsters Inc. versus Monsters University, on the left-hand side is very flat looking, right? The lighting is very flat. And then on the right-hand side, there's much more depth to the lighting. It's being a little bit more realistic as these monsters could be, right? And then The Incredibles, 2004 versus 2018, There's actually this really neat video that I wonder if I can put into the chat. Um, there's a link somewhere. I don't have the link actually right here, but if you were to Google this Incredibles 2004 versus 2018 graphics, you might get this 2-minute video that shows off a few of these things. I don't think it'll play right now. I think is it playing? Can you see it? Yeah. I won't play the whole thing, but so here in particular, you can kind of see how the shadows are much more simplified on the 2004. And as he walked through the hallway there were much more complicated shadows. And in each one of these, you're trying to notice they're modeling the real world, you know, in an animated movie that's not real, but it gives this much more depth to what's going on there. Let's see. So computer vision, right? So how does this relate? So I talked a little bit about perception already, and perception is this combination of seeing new data, seeing something new, along with what we have been previously exposed to, so that we can perceive what's happening in the scene. And that's the main idea of computer vision, okay? So in computer graphics, we often described the geometry of something and then generated the visual representation. But in computer vision, we have a visual representation. We have the new observations, and what we're trying to do is understand something about the geometry of the scene, right? So we're sort of reverse engineering the graphics problem. So things like having faces located in your camera app, right? And so you open up your iPhone or your Android phone, and it will now recognize where the faces are, so it should autofocus to where those faces are, right? And so that's one example of an output, right? The inputs are the pixels that the camera is seeing, and the outputs to the camera app is where are the locations of the faces, so that it can figure out how to autofocus. And there's all sorts of different approaches in computer vision. When I was doing computer vision as a grad student, it hadn't been totally taken over by machine learning as it has today, right? So today, machine learning totally dominates almost or most of the computer vision world, where you're essentially training a neural network system. You're doing some of the things I mentioned before, where you're essentially giving examples to the computer and telling it what it's seeing, right? So that it can learn to deal with new inputs, right? And so then you give it a new input, and based on what it has seen before, it should be able to try to tell you something that you're trying to get it to recognize, okay? But there's all sorts of other things. The basis of computer vision actually goes back to signal processing and trying to automatically do things with, say, radar signals, okay? And so that's a lot of the basis for some of the early computer vision. But then it connects a lot to doing things with like interactive robotics. One of the places that computer vision really took off first was in industrial settings. So you have automated assembly lines, and you have cameras on the assembly lines that are both controlling the robots that are like moving parts around or combining things together, and also inspecting things as they go through an assembly line. And so that was a very early success of computer vision, for one of the reasons in particular that you could control the scene very well, right? If you have a part that goes by on an assembly line, um, you can have a system that recognizes that things are the way they should be or something's wrong, right? And that's a very easy thing to do versus right now, recognize who this person is out in the street where you don't know anything about what the scene could be. That's a much harder problem in computer vision. And I'll swing back to some of these too. So some of the very basic techniques I was doing, actually even starting as an undergrad, basically taking some input images and then trying to determine what areas of the image might look like a human face, what areas of the image are moving, what areas of the image, in this case, where my eye was moving, what was the difference between those two images? And I was trying to use those to actually control a computer, and we actually made a game that you can control by moving your eyes. So you could move your eyes left and right, and that could control a computer game that had two different inputs, right? A left input and a right input, to like move a block around or something like that. Just skip a couple of those, right? So computer vision can be really hard because you might not know anything about a scene, and that's why like the um, computer vision in a factory setting is really easy because you can control the lighting, you know what's going on. But if you want to say this is actually a big problem with the Microsoft Kinect. There was a PlayStation camera as well. So all of those video games, it was a big fad for a while that you would have like motion control, you know, doing Dance Dance Revolution in your home with your own video game console, and it's trying to recognize, you know, if you're doing the dance moves in front of the TV correctly. Well, Microsoft or Sony doesn't know what your living room looks like. It doesn't know what lighting you have. It doesn't know, you know, the lighting can change between the morning, the sun's coming on one side, the evening, the sun's coming the other side. At night, it's totally different. Um, People can do weird things, right? So people could be, um, you know, standing on their hands. And so trying to recognize where people are doing things in front of a camera is actually a really hard thing to do. So the research I work in now, so this took me a while to transition through all of this. And so towards the middle of my graduate work, I actually realized I was much more interested in the problems that help people than I was in trying to do something new and neat with graphics or something new and neat directly within computer vision. And so I kind of stumbled upon unintentionally working on these projects that help people with disabilities. And so we call this accessible computing. So it's making computing accessible. And the area I work in is for people with severe motor impairments. And so there's other areas, even within accessible computing, there's large communities that are doing things for blind populations. There are other communities that do things for deaf learners. And there's even things like trying to have websites that can create avatars that do American Sign Language so that deaf users can interact with the website in what is their actual first language, which is American Sign Language versus like written English. And so it's a really kind of interesting area to be working in. So the people I work with, or the target audience of the people of the systems I'm working on, are people that maybe are quadriplegic because of a injury or a stroke or a degenerative condition. Okay, and so they might be nonverbal. They might have limited voluntary motion. And a long time ago, especially if people were born with cerebral palsy, the advice given to parents was often to institutionalize people. And it turns out this was actually pretty not okay, right? And so you know, the ability to have humans communicate with people and learn how to communicate people is really useful. But then to create computer systems that can help brings that to another level of independence. Okay, and so there's all sorts of different kinds of communication technologies that people use, and we're interested in improving them. Okay, so some examples of those. So this user here, this person here, has a switch that's mounted on his wheelchair, and so he has voluntary control of his neck, but not really of his arms or feet. And so he can move his head into that button and actually uses that with a system to type out letters and messages. And he has actually written a book, right? So he's written a book using this where the system scans along rows of letters and he picks a row and he hits the button and then it goes along the letters in that row. And so the title of his book is actually one letter at a time. You can imagine how long it would take to type out messages and books using that kind of technology. And there's all sorts of other physical devices, people that can control things with straws that you sip or puff on, some voice activated switches, etc. So the system actually turns out I'd been involved in this problem in this project longer than I wanted to give myself credit for. So this system here is called the camera mouse, and the idea is using computer vision to control the mouse pointer. And so what we're doing here is just tracking some motion of how the user is moving. So if you can move your neck and you can move your head around, then we can control the mouse pointer in a similar fashion to how your head is moving, right? And so the idea here is make this hands-free. We'll use what's called dwell time for clicking. And so you hover the mouse over what you want to click on, and when the system detects that it's been staying still for like half a second or a second, it will send the click. So we've had this system available for free, and it's on cameramouse.org. If you have a Windows computer and you want to try it out, it'll just use the built-in webcam in your laptop, or if you have a desktop with a camera, it'll use that. So you can try this out. I'm actually interested in having more people try it and let me know what you think. So I was involved in this project for a while, and for a while in my graduate work, I was trying to improve the computer vision of it. But what I mentioned about kind of stumbling into accessible computing, I actually discovered that, well, the system works okay. And we're actually interested in learning more about the users and how can the users use this system. This is actually a really interesting case here where there was a very young child who was learning cause and effect through using an earlier version of the camera mouse. So actually you see this really old camera sitting here. So this picture is probably 20 years old or 15 years old. But they were able to do some motions and then have the video game react. And so they were learning that their motions caused something on the screen to happen, which was an important learning milestone for child development, because this child couldn't play by picking things up and dropping them and things like that. So we've had many interesting student projects. So imagine for a second now, we can control the mouse pointer by moving your head, but it's not quite as stable as using like your desktop mouse or using the touchpad on your laptop. So things like clicking on links, on small links. So if you go to a web page that has a lot of links on there, it's actually quite hard to click on a small link using the camera mouse. And it's also possible you would accidentally click on something, because we're doing things like if you stop the mouse for half a second, we send a click. So we have worked on creating applications that work better for camera mouse users. And so these were all student projects, right? So this one here was a Gmail app that presented a larger interface where each of the interface elements was appropriately large for people who had the control of using the camera mouse rather than a regular mouse. This one over here is still actually something we're still developing, from an originally a proof of concept to something that is now a add-on for the Chrome web browser. And so what this project here does is it keeps track of where the mouse is located relative to the links on a screen. And so rather than trying to click on a link by directly hovering over it and staying perfectly still for half a second, what it does is it keeps a score for each link based on the distance from the mouse to the link. And so if there's a bunch of links around, each of those links will have a score that goes up as the mouse is near it. And so you just need to stay near or above the link you want more than any other link. And so in this case, say you're trying to click on the science link, you can be moving the mouse around and you're going above it, you're going below it. And eventually that science link will get the score high enough that our system says that's the one the person's trying to click on. Versus if you're trying to click on, say, the biology link underneath it, you would be hovering around that and still going over the science link, but maybe spending some more time below it. So this really alleviates this problem of misclicking a link. So misclicking a link is sometimes called the Midas touch problem, and this has to do with there's the myth of King Midas, right? So King Midas, everything he touched turned to gold, which you thought it was good to start with, right? But then it turned out to be a curse. So the Midas touch problem in human-computer interaction is this curse of accidentally clicking on everything that you touch. So this really alleviates that. And we've got this now to the point where we have started incorporating this into a web browser extension so that we can have people download it and start using it, okay? This one down here was moving menu buttons around towards so that the buttons would come towards the center of the screen rather than trying to get the mouse all the way to the corners. And sometimes it's hard to get the mouse to the corners, all right? So I'm gonna wrap up in a couple minutes to see if you have questions. I have like extra slides I could talk about. I didn't want to talk for like a whole hour. I know I'm already at 40 minutes. But we do things like empirical evaluations. So the way we do empirical evaluations is we use an evaluation tool and have the person, for example, move the mouse between different targets, and we can record the trajectory of the mouse, which is just XY coordinates. It's a sequence of XY coordinates. And we can also record where the clicks are. And so then we can visualize those as well. So we can see in this case, the trajectory of the mouse going in the order of the targets that we wanted to measure. And then we do things like calculate the movement time and throughput of, for example, using the camera mouse with a 1 second dwell time versus using the camera mouse with a different way of clicking. And we're trying to tell, is one way better than the other? And we can do things like compute statistical significance between two different approaches, right? So that's one way that we kind of do experimental empirical evaluations in this kind of research. We also will also do things like qualitative evaluations. And so this was a user who was comparing dwell time versus clicking through some other method, and they were having he was having a hard time holding the pointer still in order to click the mouse on the small targets. And so this circled area here is showing that the mouse was really moving around a lot as he was trying to click on those small targets. And so he actually preferred the other approach qualitatively, even though empirically the dwell time gave him better throughput, right, and less errors. So it was interesting that when we measure things, we say this is faster, but he preferred the other way, right? So it's useful to have both kinds of things when we do these kinds of experiments, right? So let's see, I have a few more. One of the current ongoing things I have is actually using the same kinds of mouse movement evaluation to look at how people interact with an online math tutor. And so this was the mouse trajectory of a person doing a math problem in this online math tutor that we're then incorporating in a larger project that's doing things like face expression recognition. So the math tutor can try to be more like a human math tutor. So if you're sitting with a human math tutor, they might recognize if you're getting frustrated, if you need a hint. That's what we want the computer math tutor to do. And so we're doing things like trying to measure the mouse energy over time and try to measure where in the interface the mouse is moving to try to get an idea into the system of like, does the person need a hint? Do they need a break? Are they bored? Is this too easy? Those kinds of things that a human tutor might do. Okay, so I'm gonna cut myself off there. I'm interested if anyone has any questions, and I don't know, Professor Hahn, if you had other things for them to do today, if they're trying to finish up some of the work they're doing.
Yeah, the rest of time is open time, so you can answer, have more slides, or maybe answer questions.
Yeah, anyone
Any
with
questions?
any questions?
Any new ideas?
So the neat thing is, if you're interested in this kind of work, you don't have to have like 3 years of computer science to do this, right? And so imagine a lot of the things I'm doing, we're just looking at a sequence of X and Y coordinates, right? And you can take that sequence of X and Y coordinates, which are where was the mouse moving, and you can load it up in Excel and do computations in Excel, right? You don't need to be a whiz in the high in a high level programming language, right? You can do interesting things that people in the world are interested in, just by doing some data analysis, because there's not too many people in the world that work on these problems. I actually have a project going on right now where another researcher released a data set of mouse movements, and it's all XY coordinates. And we're she did some introductory analysis on it, and there's a lot more to be done, right? And so I have a group of students who are starting to look at doing some further analysis on that. So I see a question in chat there. So if I know how similar are these accessible computing methods to what Stephen Hawking had? Um, Not the things I'm working directly on, but to some extent, there's a lot of similarities. I've actually heard anecdotally that at one point Stephen Hawking had been offered an upgraded computer that would have a more human-like voice, and he turned it down because um, he actually liked the computer he had, and I think he said that the computer the computer generated voice people identified with him, and so to him that was his voice. And so I actually find it interesting that um, he he incorporated into his persona how the computer sounded as being him, right? And so I think that was really neat. I'm glad you brought up Stephen Hawking, because um, there's a lot of stigma associated with disability, especially severe disability, and people will often think that there's a cognitive disability that automatically goes on with a physical disability. And Stephen Hawking is the perfect counterexample for people to just realize right away that's absolutely not going to be not the case. Um, there's something else. Yeah, I mean, one of the systems I was using, I don't know if I have it. Oh, I can grab this right here. So the experiment I was showing you, the results of that experiment were actually comparing camera mouse dwell time versus this headband. And this headband was developed by my co-author, who actually was a person with a severe motor impairment, that uses this little sensor. What the sensor is doing is really just and I'm not an electrical engineer, but this it's called a piezoelectric sensor, and I believe what it does is the resistance on the two leads here will be different depending on like if this thing has a little bit of flex on it or not. Okay, and so this thing he hooked this up, plugged it into a headband, and then he could wear the headband like this, and this is just going to USB. So he had a friend that could like solder those things into a USB device, and so you would raise your eyebrows, right? And raising your eyebrows would give you this signal, and when you raise your eyebrows, you have the signal go over some threshold to say send the click or do whatever. Um, so to some extent, I know towards the end, Stephen Hawking was using, I believe, like a cheek muscle twitch. And I don't know the actual technology behind how they were sensing that, if they were using some physical sensor like this, if they were, I don't think they were using computer vision. But to some extent, sending a single signal is enough to communicate, right? It's a low bandwidth communication, but it was enough. And Stephen Hawking is a great example how that was used. Yeah, thank you. Great question. Anyone else want to ask anything?
So do you have any statistics about the users of camera mouse?
Not on me right now. So we've had, I believe, 3.5 to 4 million downloads of this. And this was since that current version was released, I think, in 2008. What's interesting is the people who run the website, they would sometimes notice big spikes or bumps, and they could tell where in the world these were coming from. And so there's been several times where some article in like a local newspaper would profile someone using this, and they had people in Argentina and Brazil that the local newspaper would show someone using this, and then they would get this big spike of people going to download it and try it out. My collaborators would also get random emails from people all over the world, people from Australia, Argentina, Brazil, saying, I've downloaded and started using this. This has changed my life. Or someone saying, I'm a caregiver for someone who we're now using this together. This is amazing. Like, thank you so much. Thank you for making this freely available. And to me, that's like what computer science is all about, right? And you know, you can do something where you create something and make it available to people, and they can download it and use it. And if one person says it's changed their life, it's like that was worth it, right? You can go work at Google and improve their search engine, and a billion people use it, and that's cool too. But to me, I think it was really neat to see some of the messages coming in, that even from a few people, how important this work was to them. Oh, I think you're muted, Professor Han.
Yes, it was muted. So do you know how, like, the range of the ages of the users? How young are the users? I mean, youngest like to the oldest, roughly. And also,
Right.
what is the peak group of the users?
I don't have again, I don't have off the top of my head, but I know we've had people, children as young as 2, and they're doing things like cause and effect and learning motor skills from what they can do. There was a decent group of people who were older adults, in kind of care home facilities. The interesting thing is, deep, the demographics are all over the place, because you can have children who maybe are born with a disability, and they need to learn what they can do, and their abilities can improve. Um, you can have adults with things like ALS and MS. So if you remember the Ice Bucket Challenge from a few years ago, that was raising money for ALS. Those are degenerative conditions, and so in those cases, the motor abilities decrease and become worse. So one of the big aha moments for me was to think about how can we have interactions and interfaces that change and adapt to the user, rather than something that's fixed, rather than that something that says, like, here is how this works. You have to move according to how our system expects you to move. We should instead have systems that can change and adapt to how the user is, right? And if they can improve, then we can change it. If their motor abilities decrease, we can also change it. But yeah, I would say, you know 2 to 100. I know for sure. There's been some older people that have been using this.
Yeah, that's very inspiring. Thank you.
Thank you so much. I'm glad I was able to come in and talk to you all. Hopefully we'll see you in some CS classes in the future. So I know this was an introductory course for a lot of you, and so that we have intro CS courses coming up, and I'm sure Professor Han has been trying to sell you on on taking those. So
We haven't
listen
actually,
to her. Yeah,
we have not talked much about it. We have been focusing on App Inventor. So actually, Professor Magee is a designer of the new version of CS120. That's the first course in the computer science sequence. So could you, I know I didn't ask you to talk about the CS120. Could you talk a little bit about CS120, please?
sure, of course, right. Yeah, so this past last year, actually, we redesigned our intro CS course. Um, Beforehand, we were kind of doing a little bit of things that were somewhat like Scratch for the first half, and then we went into Java. How we've changed it now is all Python based. And we did this for a few reasons. Python's now the most popular language for almost everything, and we wanted the course to be really useful for people who both might continue in CS, so it should prepare you to keep taking more CS, but we also wanted it to be useful for people who only take that next the CS 120 course, right? And so by the time you finish the CS 120 course, we're looking at for people to now have the ability to do some things like data analysis in Python, right? And to have those skills that they could take and do something in their other courses, right? And so our approach is called CS for All, which is based on something that was developed at another university and is used by a lot of universities across the country now. So I will say it's quite a rigorous introduction. I try to warn people at the beginning. I see Claire nodding, yeah, right. Especially the first half, right, is very we throw a lot at you, okay, but I don't expect you to see everything in 6 weeks and say, oh yeah, I got that all perfect, right? And actually, I hope that the second half of the semester actually starts easing up. And I try to tell people, let's get through the first half, right? And there's a lot we throw at you, but during the second half, we're going to do some more interesting things. And the things that we threw at you in the first half of the semester, you'll become more and more familiar with. And so by the end of the semester, we have self-design projects. And so this was actually my favorite part of the course because I said, here's a list of things that I think you might be interested in doing, but you can pick what you want and you propose what you're interested in. And so people in CS 120 came up with all sorts of really interesting projects, some of which were like core computer science projects, some of which were biology related. I had several doing business and economics related projects based on things that they were doing in their other courses. They said, "Oh, I can now write a program that is interesting and relates to like this useful problem in my other course." So that was my favorite part of this semester. I'm happy to like chat with any of you if you want to learn more about how it goes. But hopefully your TAs will say nice things about it.
Yeah, thank you very much. And also, I just want to add that we'll try to offer CS 120 every semester. So even if you can't fit it into your schedule this spring, maybe next fall, think about it, keep that in mind. It also gives you the science perspective. In addition to this computational foundation that can really be used everywhere, anywhere. So no matter what your majors are, we highly encourage really all college students, all Clark students to try to develop take CS 120, just one course. One course can be really useful. Yeah. And you'll see some familiar concepts like what we have covered in Scratch and App Inventor, the procedures, the if else, the loops, and those are the fundamental building blocks. But with Python, the program can be much more flexible and much more powerful and much more general too. Yeah, it's very good. I would say not just Python programming language, it's usually computational thinking. The way you can break down the problems and systematically address, resolve the issue, resolve the problems it's very useful skill to develop.
That's a really good point. Thank you. I forgetting that you're all learning some of these fundamental concepts. That would actually be really helpful coming into CS 120. When you come in, we do the first few weeks. We're going to write functions, write if-else statements. Um, we'll write some loops and things like that. Learning what a variable is, um, learning how an expression works if you want to add two numbers together and then store it into a variable. All of those get incorporated into what we're doing, maybe in a slightly different order, but the fundamental concepts of programming actually translate from one language to another language to another language really easily. And so by having the course you're taking now and learning some of these things, it would certainly make a course like CS 120 a little bit more easy, right? Because I already told you we'll throw a lot of things at you. Well, some of them will be familiar, and that will really help. Yeah. We also try to focus on strategies for problem solving. And so the hardest thing is often not so much what do you type into the programming language. The hardest thing is often how you fix something when it doesn't work the way you think it should work. And learning the strategies to deal with that is one of the really important things that we try to have as a takeaway by the end of the semester. Oftentimes it's a lesson that's hard. It's earned, right? You earn that lesson by being stuck and figuring out that that the good strategies work well, and some poor strategies don't work so well. And I can tell you on day one, use the good strategies, but you can earn them a lot by being stuck for a while. But we really try to help you through them, right? So I know I see Jack there and Jade. We have a lot of support that we try to help, so you're not sitting there stuck for a long time, not sure what to do. So they're there to help guide you on that problem solving process. And so the idea is, by the end of the course, you have a good idea of controlling that problem solving process, so that when you get stuck, you know what to do.
So thank you very much, Professor Magee. It's a great talk and very interesting work, very inspirational too. Thank you.
Thanks so much. I appreciate it.
I hope you'll see some students in the future 120.
Yeah, I hope so.
Yeah.
Let me show you two more things, because unless anyone wants to get going. Let's see. I think I put this at the end of a couple talks just to show you how computer science really can connect to almost anything. And so this was so Bloomberg is a finance company, and they're interested in finding patterns. Right? I don't know how many of you made a lot of money on GameStop this week. Unfortunately, I didn't. Professor Han, I didn't make $1 million, so I'll still be back next semester to teach. But you could write some machine learning that could predict some of the patterns that are going on. And so they're hiring people that write these algorithms, and they use methods from signal processing and computer vision, right? So computer vision algorithms connect to finding patterns in financial data, right? And so what I talked about with the visual illusions, right? So you have a machine learning system that you train by giving it prior observations, and then you give it something new and you ask it, what are we seeing? What's happening now? So all of that is using these kind of machine learning approaches. And then this, right, our COVID-19 vaccine, right? So I'm gonna take credit for computer science for giving us these vaccines, right? So the COVID-19 vaccines are mRNA that was designed by computers and guided by algorithms. Well, some computer scientists wrote some of this, right? And yeah, I'm sure there's some genetics and biology in there too, but let's give computer science the credit for that vaccine, right? So I wanted to kind of promote computer science as being really important.